Welcome to the last meeting in the summer version of the computational chemistry class. And the goal of this class was to communicate the very basic background of the theory and get skills in operating correct software and correct hardware that would enable every of the class attendees to contribute computational characterization of molecule and materials to their research projects. During the class, we covered about 3/3 of the more serious of the regular semester class: molecular modeling, the Hartree-Fock theory and density functional theory background, and this is the third meeting when the attendees of the class are sharing the skills of operating the software targeting the fabrication of the not fabrication, characterization of the materials. So the ideal duration of each presentation is 5 minutes plus 5 minutes questions, but since the class of this year is not very big, if we slightly, not substantially, go over this limit, it will be okay. So the first two speakers are swapped because of the conflict schedule. So the speaker number one will explain how to analyze computational data that will be explained how to generate by speaker number two. And then we will go further through the practical aspects of the computational characterization of materials. So with this, I would like to invite to the stage to the stage the first speaker, Kristen Patnow. Floor is yours, and if you are okay with me flipping the slides, let's go. If you volunteer to do it yourself, let me know.
You can flip the slides if that works for you.
Okay, and please, would you please enable your camera, because it is much easier to follow the story when it is, if it is possible.
Is that on? Okay.
Okay, let's go forward.
Great. So I'm going to be presenting on the VASP output files, density of states, and total charge density. And if we can go to the next slide, I'll first give a brief introduction or kind of reminder of density functional theory and total charge density and how the two relate. And then I'll just go over the VASP output files that we're able to generate, an introduction to density of states. I believe JOYANTA is also discussing that in more detail. And then we'll look briefly at total charge density. So we can go to the next slide.
Okay.
Density functional theory, as we talked about in class, states that a minimum value of the total energy functional is the ground state energy of a system. And so the electronic charge density that yields the very minimum is then the exact single particle ground state energy. And then below that description, I actually just have a cartoon kind of that gives an idea of why we use DFT. Essentially, you take a system where you have a multi-electron system and look at it through a lens where those multiple electrons are seen as the electron density. And it makes for a more simple observation or visualization of the system when you're looking at all the electrons as one density rather than individual electrons themselves. So if we can go to the next slide, where total charge density comes into all this, it's given us the sum of orbital charge densities, and this is calculated by electronic charge per unit, either length or volume, depending on your system. But since charge density shows an electronic distribution, we can easily use it to see any defects in a molecule visually. And it's something that we can calculate using DFT. So because we have a simpler method of DFT, we can easily determine the total charge density and use that for visualization purposes of our structures. So that's just kind of my brief reminder on total charge density and DFT. If we go to the next slide, I have a list of all the different VASP output files that we get after running some simple molecular dynamics. I have 7 listed here, and I'll just go through on the next couple of slides what is included in each of those files. So on the next slide, we'll start with OUTCAR and the CHG files. And OUTCAR includes pretty much all the information that we need for everything I'm going to talk about today, with the exception of charge density. But it includes a summary of all our input parameters, information about electronic steps, stress tensors, forces, local charges, and magnetic moments, as well as dielectric properties. The CHG file contains what we need for our charge density visualization. So that has lattice vectors, atomic coordinates, and total charge densities multiplied by volume. In the next slide, the CHG or charge car file is very similar to the regular CHG file. It just also includes the final charge density, and we can use this to restart any calculations from an existing charge density. So if you want to continue your simulations from a certain point, you can use that charge car file to continue on. The CHEM676 file contains lattice parameters, the Bravai matrix, ionic positions, and it may include velocities as well. What's interesting about the CHEM676 file is that it's the same kind of format information as the postcard file, which is an input file for VASP. And so if we rename the CHEM676 file to postcard, we can use it to then continue the simulations from a certain point. That's helpful if you're trying to run longer simulations or want to see what happens at different points in the simulation. You can use the CHEM676 file and build off of that moving forward. We go to the next slide. The DOS or OUTCAR file contains your density of states and integrated density of states. Vectors, eigenvalues, and weights. And then the last output file is the OUTCAR file, which is on the next slide. And the OUTCAR file contains, again, a lot of information. I have an image below of if you were to do more OUTCAR, but it contains information regarding the number of electronic steps, current free energy, change in free energy, change in band structure, number of Hamiltonians acting on the wave function, and difference between input and output charge densities. So that's kind of a brief overview of what is inside all the files that you can get from VASP. But then specifically, if we look at density of states on the next slide, you can use the OUTCAR file to, this is just an image of all of the files together. But the next slide is going to start showing how we can use the OUTCAR file to then generate density of states. I have here just a reminder, we've already talked quite a bit about density of states, especially in the Gauss-Lee perspective, but it's just describing the number of states per interval energy at each energy level that are available to be occupied. So high density of states means that there are many states available for occupation, and the density of states that's low or of 0 means that few states or no states can be occupied at that level. So the next slide is a more practical view of how we do this with VASP. In that first, we extract our list of orbitals from the OUTCAR file, and this can be done either by the commands that I have below, or you can manually create a states file using our VI command, and use copy and paste into that file just the orbital information from the OUTCAR file. So I have an image below, and I've highlighted in a box where we see our HOMO and Lumo values. Those aren't going to come into play for the density of states process, but it's just interesting to note those as we've seen them before. Then on the next slide, we'll continue using that states file and the OUTCAR file then. And so first we'll use a variety of grep commands to find the number of electrons in the OUTCAR file, the number of ions, our Fermi energy, and our alpha plus beta energy, which are all going to come in handy as parameters that we set when building the density of states file. So I have an image below again, just showing the practical commands using Cori, and I've highlighted all of the resulting values. On the next slide, we get to the essential command which we use to generate that density of states file. It's that bin-res-dos norm, which is going to prompt you to fill in a number of values that we just determined using that OUTCAR and states file. It's going to ask for minimum and maximum energy, which are the first and last energies in your states file now. So the very first orbital's energy and the very last orbital's energy. The number of states is exactly that number of states in your states file. Fermi energy, alpha beta energy, number of atoms and number of electrons. Again, we just found those previously using the direct commands. And then after entering all of those, we're going to enter one more time on the next slide. You'll end up with an output. Oh, yeah. So then I have here just an image of me doing this practically, and as it prompts each value, I enter them in sequence, no sooner and no later than they're asked for. Otherwise, you have to start the whole process over. And then at the very end, it says that the DOS Fermi file has been written. And so from there, we can then start to generate that as a PDF. If we go to the next slide. Right now, we have the DOS Fermi file, and you can hit more to open it, but it's not going to be too helpful for a visualization purpose. But once you open it, you can look through it if you like, or close it right away with a simple click command. And then we use the new prog to generate the DOS in a PS file, and then use our PS to PDF to write command to finally convert it to a PDF, which you can then copy to first the Photon server and then your local computer. And on the next slide, I have it opened in this Adobe Acrobat viewer, what mine looks like. A little bit of a wider x-axis than I needed, but you can see both the unoccupied on the right and the occupied orbitals on the left-hand side where that purple is. And obviously, depending on what values you put for your minimum and maximum energies, you can shrink or elongate that x-axis, and the y-axis is just showing our density of states. So that's how you generate kind of practically the PDF of your density of states, and you can visualize that pretty easily just using that OUTCAR file, and then a few simple commands in Linux. So then if we move on, the next slide starts to talk about total charge density. And this process is basically just a visualization using VMD software that I use to transfer your postcard and charge card files to your local computer. Since they're in Cori, you have to copy them first to Photon, and then your local computer, and then open them both as new molecules in VMD. And they have their own specific file type. They're VASP postcard and VASP charge card. Those, in my case, didn't autofill, so I had to manually select them, but you'll want to make sure those are correct in order to visualize properly. And then in the next slide, I just have kind of what you'll end up seeing after those are chosen and your graphical representations have been chosen. I used van der Waals, dynamic bonds, and solid surfaces so that you can see the kind of molecule. It's in all red. It's essentially just the molecule. And then when you have those gray spheres on top, it's also highlighting those charge densities within the actual molecule. So that's a pretty simple tool to use just to easily visualize your charge densities. And like I said before, because charge densities related to, so we can calculate charge densities in DFT, we can then view it, and then if we see distortions in our structure, we can usually notice where errors are happening in some of our files. And so then the last slide is just a summary of essentially what I already talked about, and then a brief, since it is the last presentation of the summer, what I learned from the summer that I'll be using in my own research. Using Linux commands, we are able to run microdynamics on our molecules that give a lot of different alpha files that we can use for a variety of different visualizations. In my case, we look specifically at density of states and charge density. And then of our course materials that we covered all summer, the most, I think, applicable to my own research is going to be the optimization and visualization techniques. I have here on the right an image of some of the molecules I use for my work. And this is a protein with the ligand docked to it, and so I want to do some work with individual optimization and then optimization of the entire dark molecule to see what's happening to the change in my energies, whether the ligand is attached or not. But that's all I have. I see there's some questions already. So.
Okay, please join me in thanking Kristen for important and substantial presentation. And now questions are welcome in both verbal and typed forms. So there are 3 or 2.5 questions. So if the author of the question doesn't want to speak it up, I can just read it. So Mary Mel is asking which. Okay, now there are 4 questions. So which states in the density of states are usually most important when analyzing occupied and unoccupied states?
Excuse me, am I understanding the most important when looking at density of states are going to be your HOMO and LUMO values so that you can see where that change is happening from occupied to unoccupied orbitals.
Okay. And the next question from the same visitor is, should we care about much deeper states? Yes or no, and short reason.
I don't know if I understand what you mean by deeper states.
Okay, I'm going to bring up your slide with example of density of states. Mm-hmm. And one can go at, like HOMO and LUMO in your case are at -5 and 0. And the question is, should one, is there a reason to explore states at -25 electron volts? Do they contribute to any processes in chemistry or in material science?
I would, I'm not entirely sure, but I would have to say, I think yes, when we're looking into excitation and emission.
Which excitation emission in which range? Like if you go from infrared, visible, UV, X-ray, gamma rays, in which range lower states are important?
Lower states would be more important in like your IR and. No, the other way. I'm sorry, I'm blinking out the name of it.
So it is higher excitation energy when it is between UV and X-ray.
Yes, thank you.
Okay, so let's quickly go to next questions and then to the next speaker. So Javed Mohammed is asking, I am just wondering that the shown calculation is a real model system. Why is the Lumo energy positive?
Yes, and the answer to that is it was a real system, but I found out after generating the files that my OUTCAR file had an error in it, so the elements and numbers are not actually correct. So if I were to redo this with the actual model, you would have a negative Lumo energy. Okay. I found out yesterday it was an error in my file.
Okay, and now there is a killer question from Professor Kilina. So, what is energy cutoff? So it is not. It was not delivered during the lectures. So you may try to go to Google quickly, or just try to connect your memories about basis states with this question.
If I remember correctly, it has something to do with fixing a number of plane waves in a basis set.
Excellent, excellent. Yes, yes, it is a maximal energy for which states are still included into the plane wave basis set. Okay, yeah, it was moving into the right direction. So any questions to Kristen, anyone, or comments? If more questions one, more questions two, more questions three. Okay, let's thank Kristen once again. And let's go to the, thank you, Jayanta, for your comment. So the presentation by Lixue Sha. So I want, before, Lixue, please prepare your camera. It will be much easier to follow what you present if you enable it. So Lixue is the summer visitor to the University of North Dakota, and in a frame of collaboration between NDSU and UND, he was visiting this summer series. So, Lixue?
Yes, can you hear me?
Yes.
Okay.
And I'm showing, you were not updating slides. I'm showing if you were sending something in the last an hour, I need to quickly bring it up, or you should share. But if it is the old version, is it okay?
Yes.
Okay.
Okay.
Yep. Please go ahead.
Okay. I need to share my screen, right? Okay.
I can share if it is the same slides. I can keep sharing, but if you are changing slides, then please share the screen.
Just a little change because of I successfully submit the job and it really works.
Okay. Okay. Yes. Please share the screen then.
Okay. I will share the screen. Thank you.
So if by some reason it doesn't work, just quickly send me the. Oh, it works. It seems to work.
It works. Okay.
Yes. And you may go to presenters view.
Okay. Hello everyone, I'm Lixue Sha, a visitor of this course, and today I will give a brief review of DFT input files. Just we all know that we need 5 files to complete VASP calculation, including the in-car, post-car, decoys, and script to submit the job. So first, we focus on the in-car and the function of the in-car. The in-car file holds the input parameters, which is still the calculation. I usually divide the in-car to 4 parts. The first part is the global parameters, which control the whole calculation system environment of the calculations. And what matters is the parameters I usually to change when I deal with different systems. The first one is iSpin. I would like to change the iSpin to 2 when I deal with a system, when I deal with magnetic systems, which usually contains the transition metal, such as the iron or cobalt. And the second one is ENCUT. It is just the question mentioned. This is the energy of the cutoff. It's about the is the cutoff energy for the plane wave basis set. When we increase this number, it will increase the calculation accuracy, but at the same time, it will cost more expensive calculation results. So we should set this number carefully. And one thing that we should take care is that the value of the in-car should be equal or greater then the max value of the index in car, and in that, so that we can get a reliable calculation results. And the next one parameter I usually to change is that the L wave and L charge, especially when I like to do some multiple calculations, such as accurate projection of those, or when I want to get a BSE optical properties, which all need the wave car of wave car and charge car of previous calculations. And if we don't want to use it, just turn it to false. And the second part is about the electronic relaxation. It's just about the electronic convergency, the same minutes. And in this part, I usually change the NELM, which means the next step of the electronic convergency. And if we dealing with a system with a bad initial structure, this could help us to get a convergency in electronic relaxation. And the next one is NELMN, which means the minor step of the convergency. It also helps to the structural optimization, which will gives us a more accurate wave car for next structural optimization. And EDIFF is also an important one. When we want to get an accurate structure, especially when we want to calculate the final spectrum, that will help us to get a really accurate structure. To set it at -8. And usually when we set it at -5, it's also okay to get a stable structure or reliable structure too. And the third part of the ENCUT is that ionic relaxation, which control the structure optimization. The first one is the unoccupied, which control the step of the whole structural optimization usually. And the second one I used to change is ISF, which control the stress and relaxation of the atom and whole structures. When I set it to ISF to 2, which means that the position of atom changed, but the crystal parameter will remain the same. And if I change the ISF to 3, that means both the atom and the parameter of crystal will change at the same time. And the part 4 of the keywords is about the special property. In most calculations, we want to get the special property of the system. And the first example is the calculation of partial density of states. We need to set the I charge to 11, which means to read the charge car get from previous calculation. And then we need to set orbital to 11, which means to calculate the projection of density of states. And example 2 is about the electrical field, which I plan to do a job about the electric field. We need to take the electrical field into consideration especially when we deal with the system, such like electronic catalysis, which include three phase, include the solid phase, gas phase, and even liquid phase. So the electronic field should take into consideration, and we could set a null dipole to choose to start electric field calculation, and then we can choose the number of the I dipole to set the direction of the electric field, and then we can also set the field intensity by the E field. And the second one is the postcard. And the postcard contains the information about the structure, especially the position of the atoms and the parameter of the whole crystal. The step I usually prepare the postcard for the VASP. I usually to build a mode by the Material Studio and then transform the mode to the postcard by the scripts created by Professor Yan. And the content of the postcard, we usually have about 10 parts of the postcard. And what I think is most important is that we could change the reaction state of the all atoms to change the T to F to fix or to relax the atoms. We can. And the picture at the right of the slides, we can see that the free one is the atoms that the picture at the left of the slides is that the carboxyl dissolved on the copper surface, and the left one, free one, means that the carbon atom underneath is relaxed and is free to relax, and the right picture of it, the red atoms means that the carbon atoms beneath is fixed during the structural optimization, which all we can achieve by transfer the T to the F of the respective atoms, and we can also make it by the script created by the Professor Yan. And the third script is key points, and the key points file determines the sampling of the first Brillouin zone, which also contains 5 parts of the key points. The header is about the command of the file, and the second one, 0 means the automatically produced file generation scheme, and the third one is about the grid type. In this key point is about the Monhorst-Pack grid, and the fourth is the number of the subdivisions in each direction. This choose one we usually to change to change the accuracy of the simulation calculation. When we change these low numbers, such as 111, the calculation will be no accuracy. And if you use the number with 771, a higher number, which will get the high accuracy of the simulation. And then is the podcast of the input file. The podcast file contains relevant information concerning the pseudo potential that are necessary to run the calculation. In the cluster of the UND, I can use the choose command to get the podcast of respect items to the podcast we use to use for the VASP calculation. What we should take care is that the screens of the postcard should be consistent with the elements in the postcard. And when we do that, and we can use script TIT postcard to look what kind of postcard we use in the whole postcard. And then there are examples couple of postcards. We can find some very important information in postcard. The first one is the number of the valence electrons. And we can see that the copper electron in this postcard is 11. And the atomic mass of copper is about 63. And the index equal to 295. And just like what I said before, the index of the postcard beside the cutoff energy in the ENCUT file at some extent. And the third one and the last one is about scripts to submit jobs. We should also changed in rows, who means the number of the compute rows per job. And the next one we can change is the n-task per node, which corresponds to the number of calls on the computer nodes. And the third one is the time of the whole calculations. And I used the script listed before, and I submit a job in the cluster, and it works just like this one. It's running now, and that's all. Thank you.
Okay, yeah, please join me in thanking Lixue for a very detailed presentation. And now there is a, please keep your slide, maybe someone will want to ask a specific question. So it's time for questions either by verbal, speaking to the microphone or typing. And by now there are 2 questions in the chat line. First one by Professor Svetlana is what is direct coordinate system? Like direct versus Cartesian.
Oh, Cartesian. Oh, that's the.
So can you please show the slide with your postcard?
Yeah.
Yeah, and now please explain.
Cartesian. This is direct. And Cartesian correlation is the real position of the atom, which are not converted to the fraction coordination.
Okay. So you are telling that direct is fractional coordinates.
Yeah.
Okay. Good. Thank you. And there are a couple of questions from Professor Khang Hoang. So, wait. Fraction of what? Lixue, can you please explain about fractional coordinates? Fraction of what?
Fraction of the whole parameters of the crystal.
You mean size of the unit cell?
Yes.
Okay, good. And what is the size of the unit cell for the model that you're showing? In which part of the postcard? Huh? Which part of the postcard should we look for the size of the unit cell? Can you show by your mouse?
I beg your pardon. Could you speak again?
Yes.
Which part?
Which part of the postcard file tells us about size of the unit cell?
Okay, I'll show you. You can see the number in
yes.
the line 3. Is that right?
Uh-huh.
Yeah.
So line 3 to 5, right?
Yes, line 3 to 5.
Okay.
Which represent the 1 parameters of the crystal.
Okay. And there is another question. Please name the lines. Like what these numbers in lines from 3 to 5 mean?
These lines the parameters of the whole cell, such as the A anxious and B anxious and C anxious.
Okay. 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 So lengths, dimensions in X, Y, and Z, right?
Yes.
Okay.
Yes, X, Y, Z.
Yep. Thank you, Lixue. And there are questions from Professor Khang Hoang. So he's answering, asking, what is the difference between Monhorst-Pack 771 versus Gamma 771? So it's a question about K points.
Yeah. Oh, sorry, I'm not very sure about that.
Do you expect that calculations will give different results if you change this keyword Monhorst-Pack to Gamma?
Yes, I think they will remain the same, the results.
Okay, okay. Professor Khang, would you like to give the key to quickly answer yourself to Lixue? Okay, so for odd grids they are the same. So it will make sense if the number of the K points is even.
Yeah.
And there is one more question from Professor Khang Hoang. How do you decide the value for ENCUT?
Okay. I usually ENCUT, just as I said, you usually have to set the ENCUT equal or greater than the max value of the ENCUT in the postcard. Just I mentioned in this place, there is a max of every of respect items in postcard, right? So the ENCUT should be larger than the max number of the index in the postcard. And if you want to get accurate calculation results, you can use a value equal to the 1.3 times of the max index in the postcard.
Okay. Yeah. Thank you. So yeah, Professor Khang Hoang, thanks you for the answer. More questions to Lixue? More questions 1, more questions 2, more questions 3. Okay, let's thank Lixue once again.
Yeah, thank you.
And
Yeah, sorry, Dimitri, I just want to weigh in. I think this Lixue is the first presentation in the United States, and this thank you so much to give him this opportunity.
oh, okay.
And, I think he did a great job, and I learned a lot from this. I mean, again, thank you, and other professors' question here very helpful. Very helpful for him.
Thank you, Tao. Thank you. It's Professor. It's really great. I'm also happy for this opportunity. And now let's go to the presenter number 3. Lixue, you may yes. Thank you for stopping the sharing of the screen. And the next presenter is JOYANTA BANERJEE. Would you like to share the screen, or would you like me to flip your slides? Okay. So, and JOYANTA, please consider to bring to enable your camera. JOYANTA, are you here?
Yeah, it's not working. It's not working here.
Okay, yeah, let's go anyway.
Yeah, anyway, just wait. Yeah. Today I'm going to present molecular orbitals by BMD. Next slide.
Oh, sorry, it stopped sharing. Just a second, it will come back. Yes, I think it should be. Yes, we'll go ahead.
Yeah, so BMD uses several different GUI forms. Each designed to control the specific aspect of the molecular display, like to control the appearance of the graphics display window or to change the colors of displayed objects, like several aspects. And each form has a unique name, like includes a button, which is the name of the form near the top of the window. Let's think this button will hide the form from view. The following sections, like using your mouse, you can do it and you can represent the brief description of the forms available in the BMD. The remaining things that you can do by transferring your files to your local computer and into BMD. Next slide. So BMD main, you can select the file here and select a new molecule that you want to transfer from your local computer to here. But previously you have to write several scripts, like several commands to come here. But in BMD main, you can represent the new molecule and its structure, like Lumo and a lot of. So here first I started here file and then go to new molecule, and new molecule means file name, my name, and CHEM676. So you have to browse it here, and then you have to select from your movie.xyz or OUTCAR files. From your files you have to choose, like portrait postcard. So first I have chosen here postcard. So first file, go to new molecule, and then new molecule's file name users your name and that subject, and then go to the directory and then postcard. Select postcard. By selecting postcard, you have to select files of type, and you have to select all files. And the determine file type that I'll discuss later. Next slide. So when you come here, then file ID0 TADF postcard file atoms frames volume, then load files to postcard. Determine file types all. You have to select it from automatically, and then file molecule graphics. Then you have to come to graphics. So graphics, there are a lot of options: representations, colors, materials, layers, tools. Then you have to choose representations. Next slide. Then graphical representations. Then you come postcard file, right? So then you have to choose from selected atoms, draw style, selection, trajectory, periodic, coloring method, material, then drawing method. So then after that drawing method, you have to choose dynamic bonds. Next slide. After coming here, create dynamic bonds. So you are completely from your files, you are viewing in 3D. Like XO is in 3D mode, you are viewing complete the molecule, the structure. So then some selected atoms coloring method that I will discuss little bit later. Drawing methods, dynamic bonds. T4 distance cutoff. Distance cutoff you cannot increase bigger because it will destroy the complete proper structure. So the what you have to do, you have to minimize, like you have to optimize it. So I have already chosen here 2.0, bond radius 0.3, bond resolution 12. So then next slide, I will discuss later. So when you come here, then you have to choose dynamic bonds and drawing method. You have to choose BDW. That's very important. And then material. Material means I'm now here choosing opaque and sphere scales. Like sphere scales is very important here in VFD. You have to properly, you have to optimize it. Like I'm choosing here 0.3 and sphere resolution like 12. So dynamic bonds, BDW, and then sphere scales. Next slide. Next slide. Then when you have to go back, then you have to choose further BMD main because you have chosen one directory, right? So then you have to create new molecule. So then coming to new molecule, you have to come back to BMD main. Then you have to choose the file new molecule. Then next slide. The new molecule file name dot charge 0040 means that is your HOMO. So HOMO you have to choose it because we are here discussing the orbitals. So HOMO and Lumo, that's important. So HOMO orbitals you have to choose port charge, that is very important because after postcode you have to choose port charge, then file name browse, and then go to the determine file type and then load and VASP departure that you have to select. Next slide. And here departure 0.00 means that from HOMO, you have to select it here. Then ISO surface, coloring method, drawing method, and ISO value, and range, volume. Volume is okay, and draw. From drawing, you have to choose from points to solid surface. That I'm representing a little bit later. But here you can your eyes you can throw this you can see like draw solid surface. You have to check it here properly. From points you have to come to solid surface and then range and ISO. So range means that button that below that ISO value button, that is important because that will completely determine your proper and optimized structure. Next slide. Here, in portion 0.0040 means like HOMO orbitals, I'm showing here, and then from solid surface, you have to come here and coloring method you have to choose. Coloring method means you have to choose color ID, and then and range, I already told that range means you have to choose the proper button here and proper optimization button. You have to choose it like left, completely left you have to go, and then you have to optimize the ISO value and range, and then from color you have to choose, like I'm representing here, that is homo. So homo is like blue 0, and then mm, color ID and volume. Next slide is homo orbitals, and then from Lumo orbitals you have to show right after that. So same thing you have to repeat. Like you have to go new molecules, and then you have to repeat things. Torture 0.41. You have to collect from your transfer files, like after postcode, torture 0.40, and then after that you have to come to Lumo. So Lumo orbitals, then select a completely from your files, and then you have to choose color ID, and then one. One means here the red. So several colors are there. So after representing blue, I'm coming to red. So red here, this is representing as a Lumo orbital. So then the material is opaque same iso surface. Then you have to optimize properly here iso value. Like you have to completely not very right. It's a left and little bit right. So then step 1, draw. Obviously, you have to come here from points to solid surface. Otherwise, what will happen? You cannot draw properly. And then apply changes automatically. Then heat just apply. Next slide. 3D, you can visualize the complete molecule. Thanks so much.
Okay,
Any questions?
please join me in thanking Joyanta for a very visual presentation. So questions are very welcome, either by words or in the typed way. So questions 1, questions 2, questions 3. Oh, Jabbat is asking how can you visualize allk file? Joyanta, do you understand the question?
Yeah, a little bit. The visualization is you have to transfer from your Dr. Dimitri describing complete things previously. That's why I have taken from like our class materials, and then you have to visualize it properly. Means like through your homo and lumo structure, like that already through your color ID that already you represented. Means that's from there you have to check it that it's proper. That already you from class that I already I transferred the files, like from Parchurch 40 like homo and 41 like lumo. From there you can directly visualize the homo lumo, and later also you can calculate the energy gap through other methods. I don't know here how to do it, but through homo and lumo you can visualize the proper structure.
Javid, are you satisfied with the answer, or your question was about something different? You can either speak or type. Okay. So let me complete this one. So Javid, just to finish discussion, allk, it does contain coordinate, but Joyanta was showing that first he was plotting the structure, and then on the top of the structure he was downloading the partial density distribution. So it was two interlaced images. There is a question from Professor Khang Hoang. Let me read. Is there anything that VMD can do that other tools like Vesta cannot? For lots of tasks, Vesta is much easier to use. It's okay if you don't know Vesta and do not know the answer. And Joyanta, please feel free to answer, and any other class attendees are welcome to contribute to the to answering this question, especially Jenise. Joyanta, is there any comment in reply to Professor Hoang?
Yeah, BMD is I think it's a visual molecular dynamics, right? So I think it's good. So anything that BMG can do, maybe means like it's special things like VASP and electron density.
Wait! You already told, JOYANTA. You already told from the name of the code.
Yeah.
So it's visual molecular dynamics. I think it is
Yeah.
an answer for. Yeah.
Only you can
And-
visualize the molecule. That's the important thing. 3D in 3D. But in VASP, what you have to do, you can just electron density. You can calculate, right?
Yep. And
Yeah,
Dr. Yulun Han is answering. So VMD is much easier to create movies with. More questions
for
to.
visualization, it's good. I think for visualization, it's a very good. For UIC that developer, it's very good.
Okay. More questions to JOYANTA? More questions 1? More questions 2? More questions 3? Okay, please join me thanking JOYANTA for very visual and helpful presentation. It will really help most of us in the future career. And please, Mahima, please prepare to present. Please consider to enable camera if it is possible. And I can flip your slides unless you vote to flip it yourself.
The camera is on, no?
No?
I need to disconnect and...
No, do not waste time. If it doesn't work from the beginning, we'll try to follow. And please tell me when to flip the slides.
So, good evening, everyone. Today I'm gonna...
Just wait, just a second. If someone has microphone enabled and is typing something, please mute the microphone, because to avoid additional noise. Thank you. Okay, Mahima, please continue.
Good evening, everyone. Today I'm going to present about the UV visible spectra using VASP. And if you guys are wondering what kind of quantities can VASP calculate, so from VASP we can calculate total energies, forces and relaxed structures and band structures, and dose and projected dose, that is density of states, and magnetic properties, and optical properties. Optical properties, that is absorption spectra and dielectric functions, like that. So for setting up a VASP calculation, you need 4 input files to run a calculations, that is postcard, portcard, and key points and ENCUT. Next slide. So here I will just showing how to calculate these in our photons. Next slide.
Just yeah. Am I showing the right slide?
Yeah, this is the first one.
Okay. Is it okay, or should I go to the next one?
No. So here the findings simulated spectra with VASP. So first you need to log into our photon or whatever the system you have, and you need to have some commands that you need to follow, and then you need to go to this Cori directory, and you can see all those postcard and all the VASP files. And next slide. So here you can see the states, and there are some errors also happen when I run the calculation. And you'll see the band number, band energies, and occupations for these calculations. In next slide, you'll see the next slide. Okay, so I think this is just zoomed in. We'll see the command for the... I think something happened with my slides. It zoomed out. Okay. Oh, next slide. So here you can see the states that are band number, band energy, and occupations. So first band number is 1 and the last one is 46. So I just cropped it and put it in there. And next slide. After finding head and tail of your energy system, you will get these many values. And these are the input and output files. And next. So you can see the XYZ of your particular file. And next one, this is the set of the files that we created, the new directories and the VASP directories you can see from this one. Next one. So this will explain next couple of slides. So you will get these after running the ostrength command. Next slide. So to the summary, so the multi-electron observables can be often represented in terms of one electron matrix element that is shown in the previous slide. In next slide, I will explain a little bit more. So next slide. These are the values, that is initial, final from that equation, and intensities and energies. The red color ones are the intensities for the energy intensities. And next slide, these are the main direct commands that I used for run this job. And next slide, you will see the parameters for the spectra. So in third lines, you can see the number of transitions, that is 640. So after running this experiment, I will get the 640 lines in this spectra. So, and then you can put minimum and maximum energy differences. So I put 0.1 and 8, and an electron volt I put like 0.1 and 40. So, and after that I will get the spectrum. So you can see in that there is new directory is formed. So after we get the spectra, you can go to the head spectrum and tail spectrum. You can see what we done, and you will get the UV, and so the new directory is formed, spe1.ps. So that is our UV, I guess. Yeah, yeah, that one is the UV. And next slide. And after we get all this UV and visible spectra, you can convert that into PDF. That is the command the command is here. And after you done this job, you can download this PDF and we can see what other changes happen in the next slide. So these are the frequencies for the visible and ultraviolet spectroscopy. Next slide. So I'll get this for the UV, and you can see the UV start from 400 nanometers. So I'll get the exact one here. That's the output. And so I tried the titanium dioxide. You can, next slide. For the titanium dioxide spectrum, this is the computational one. This is the experimental one. You can see the differences, 350 nanometer. Next slide. This is the visible one. So visible start from 327. So you can see the electron volt. So this is what I did for running this. Thank you.
Okay, please join me in thanking Mahima for being brave and taking this complicated subject. And the questions are very welcome either by pronouncing them into microphone or typing in the chat line. So there is a question from Professor Svetlana Kivina. I'll read it out, and Mahima, you may start thinking how to answer. The interaction of the electronic wave function of the system with light results in redistribution of the electronic charge density at the excited state compared to the ground state. Is this effect included into VASP calculation of the spectra?
I'm not sure. I think yes. I think this will be included in the VASP calculation.
Okay, okay. Do you think it is taken in, it is included in full or partially, or?
Okay. What was that? Sorry?
Do you think it is included in full or only approximately to the certain extent?
Certain extent.
Yes. So the upon what you were reporting is independent orbital approximation when orbitals and charge density from which they are derived are not changing completely. But when one is promoting electron from occupied to unoccupied orbital, overall density is expected to change. So it is partial account of the effect that Professor Kivine is mentioning. Next question from Mary Mel. What is oscillator energy, and where would one find it in the output files? And how would one visualize it in the spectra?
So oscillator energy, I think.
Wait. Before answering, Mahima, before answering, please tell. Do you like the terminology? Do you like the word, the term oscillator energy, or you would prefer something different?
Oh. Oscillator energy. I think.
Okay, oscillator strength. Now the Mary Mel has corrected oscillator strength. Okay, please continue.
So the oscillator energy. So it's the probability for the absorption and emission spectra.
Very good.
So there will be energy levels in the electromagnetic radiation transitions, right? So in an atom or molecule, so that will express the probability of. Okay.
So let's finish the this.
Okay, yeah.
This one.
Let me read the questions once again. And where would you find in the output files, and how would you visualize it? This vector.
So in the output file, it is the third column, and in the spectra, how does like which feature of the spectra should one look at to find correspondence to oscillator strengths?
It's in the. So in this 0.35 at top.
So you tell that height corresponds to.
The height in electron volts. So
not in absorbent. Okay, height corresponds to oscillator strengths. Okay, I think it is thinking in the right direction, and Mary Mel should be happy with the answer. I hope. Now, next question from Professor Khang Hoang. How the number of K points and value of N bands may affect the calculated optical spectrum? This is the challenging question. If you have any comments, please answer, and I'll help after. Mahima, do you think that making computation with larger number of K points will make the spectrum more precise? Just say yes or no.
Yes.
Okay, very good. And then Jenise is just giving you a credit, and then would you know a way to show this photo excitation using movies?
I think, yeah, we can.
Jenise, it is possible, but it is quite hard. One needs not to make movie not of the atoms but of the orbitals as they change in time. So it's.
There will be like molecular movies, right?
But instead of atoms, there will be charge density or orbitals moving in time. So it's a hard task for visualization. More questions to Mahima. More questions 1. More questions 2. More questions 3. Let's thank Mahima once again.
Thank you.
And now, last but not least, presenter Jenise. So if your facility allows to enable camera, it will be a plus. And switching on the microphone is not optional.
Yeah, I know. Sorry about that.
If you can, if it is possible, please turn the camera as well, because it's.
Unfortunately, my camera is not working today, so
okay.
I will be unable to do so. But I'll try and figure it out for the next presentation if I can.
Okay.
Alright, so I have done my presentation on VASP, molecular dynamics and heating, particularly of how to create these sort of scenarios in input files, how to calculate these exact interactions, and exactly how these molecular dynamics are made. And mind you, this is a very broad overview, considering I have to talk about quite a few topics that were covered in previous presentations that they could have done in a lot more detail. So thank you to the previous presenters and their information that have helped me sort of create this presentation. All right, next slide. So we'll be talking about in this particular section thermal heating and file prep for just showing where the molecular dynamics, or at least like the calculated molecular dynamics, are sort of concentrated, and how exactly to cut these files for a batch job. Okay, next. Firstly, we start with file modifications for the heat process. So you're going to have to input the valid OUTCAR, POPCAR, quality debug SH, and K-point files in order to properly run everything, as these files contain most of the information about the molecular structure that you're going to need in order to actually properly calculate the interaction described. Then you can copy an in-card blank slate from a proper directory, or make it yourself, either one. I particularly copied this from one of Dr. Keelan's blank slate bins, and once it was copied over, I was able to change whatever sort of parameters I saw fit, as Lixue had described in her presentation, or sorry, his presentation.
these sort of modifications can change temperature, what sort of magnetic field we would be working with, different things such as step size, how many steps, convergence size, temperature, etc., etc. And those are just some common modifications. There's plenty of other modifications that you can do in order to sort of start these computations and go through with whatever you may need for your research. All right, next slide.
Just a second. Out of the way. Okay.
Okay, so for submitting a job, once all files have been copied over and edited, job based on UTCAR's modifications can be submitted. This is always a batch job based off the Core debug sh file that you have in your directory. Otherwise, you can't really submit a job unless you make a new Core debug file. And once you have that, you can submit sbatch core_debug.sh, and that will submit a batch job according to your inputted values and parameters. And it will take a little bit of time, but as soon as the queue is in line for you to get your job completed, then your job will complete, and the files, all the necessary output files will be found in your directory. Okay, next. So here is the main molecular dynamics. So what heating mainly affects, at least in the kinetic theory of gases, is temperature is related to kinetic energy directly. And so by having a temperature graph, you can show exactly what sort of kinetic energy you're looking at least in the terms of motion of the molecules. Anyways, that's going to be in your simulation. You can also use more accurate theoretical frameworks depending on what sort of inputs you have and what sort of actual programming you put into it. Though most commonly, for very sort of quick and easy calculations, kinetic theory of gases is very easy and quick to do computationally. Additionally, on the code side of things, you can see a lot of the sort of velocities in the OUTCAR file and a couple of other parameters noted in the OUTCAR file, which you can sort of allow for visualization of heated or the heated system. And this is shown at like each time step. So given the time span, you can get more and more velocities that are more and more accurate progressively up to a point where it's a very smooth and accurate simulation. Okay, next. So how we can visualize these molecular dynamics for the most part. These are only the two ways that I personally know. There are plenty of other ways that you can visualize molecular dynamics. These are the two main ways that I've done and are particularly necessary for what I'm interested in. So for temperature versus time graphs, this can show a lot. Oh, sorry.
Sorry, just a second.
Oh, no worries.
It just jumped. Okay, please continue.
No worries, got them. But so one way you can do this is you could create a GNU plot of temperature versus time. So this can show often these sort of movements of a molecular system, given what sort of format you're programming in at least. So let's say that you had a similar system to what we were doing in class, such as the which is really close to the structure on the right here. Essentially, you would end up with if it's a very, very basic temperature graph, you'd often see these jumps going back to this one sort of temperature, which is often the temperature that you set at, and then it'll gradually decrease. These sort of like bumps happen, and so once these bumps happen, they typically sort of relax because a lot of the energy is being dispersed into potential energy. So once that potential energy sort of goes down, then it bumps back up, the program bumps back up, and then it can go down again. Or you can do something a little bit more complex like this graph shows. I'm not specifically sure what sort of system this is showing, but it was more as an example than anything. And the next way to sort of show molecular dynamics that's particularly interesting to me at least is molecular movies. These show molecular velocities by using data formed by calculation, and often this is just exported as a .xyz, and you can put it into VMD or Avogadro or VASP or not VASP, or Vesta or any sort of program you'd like, and you can actually show a sort of movie and how it progresses. And this can often be for basically whatever sort of system you want, depending on the inputs you put in, of course. All right, next. Now that we've had sort of a brief overview of kinetics of molecules, at least regarding to simulations, we'll now start to look at molecular movies and those simulations and how to convert files that you may get to proper files for upload, or where to upload them and how to visualize them. Okay, next. So here are two programs that I particularly use. VMD, which is drag and drop format, allows for a lot of analytical tools. These analytical tools are much more robust than things like Vesta or Avogadro, as you can often, sort of simulate a lot of environments, or you can analyze certain settings or parameters of the simulation that you're typically not able to do with base packages of Avogadro, Vesta, etc. And as such, VMD is very, very robust for movies, and as well as making these molecular movies and analyzing them. So it can be very, very useful for that, though it often sometimes lacks visual quality, whereas things like Avogadro appear more user-friendly and have a bit of a better visual interface. But also Avogadro, to that extent, does not have a very robust analytic tool set. As such, you have to add extra extensions to actually properly get these analytical tools, rather than just getting them right out of the box like with VMD. All right, next. So there's two ways you can actually convert a movie. So for one, you have your movie.xyz file that you can SCP directly to your computer or directly to another server, then to your computer, depending on how you have things set up. But in this case, we start a movie off as a .xyz file. Unfortunately, those are unable to be uploaded as a video into any sort of video editing software or any sort of video sharing website, such as YouTube. So in order to convert that, you can do one of two things. So you can screen capture. I have a program on my computer called OBS Studio that can screen capture and allow me to show the movies in things like Avogadro or VMD without sort of compromising the UI and any sort of analytical tool sets that I may want to show in my video. However, a much more quick and easy way to do it is to just do a .xyz to .mod conversion used by your specific cluster. In this case, I use the command used by Quarry in order to convert a .xyz movie into a .mov movie, and as such, then it can be uploaded, to whatever sort of platform you'd like. Okay, next. And just as sort of a quick overview of how to, sign up for YouTube and sort of upload these videos, all you need to do is simply create an account, which all you do is just click create account on the sign-in page, and you'll follow the prompts and your account will be created. Once that's done, all you have to do is go to the top right corner, click upload video. There may be a bit of a couple of steps in between that, depending on what sort of account that you're using. But once that's all done, then you're able to upload the video just by simply drag and drop or another form. It will take a while to process. I've had several videos that have taken upwards of, hours to days. And as such, some patients needs to be exercised, but it's fairly easy in that all you need to do is just drag and drop the file that you wish to use and simply continue on. Okay, I believe that's it. Yes, the extra part. So this is just sort of a example of a molecular dynamic model or movie, and it shows essentially an optimization of a molecule in a certain temperature, or either that or it's going through thermal equilibrization. But essentially, this is just sort of an example of what kind of movies you can put up, and this one is particularly from BNB. So,
okay,
that provides most. Yeah.
Please join me thanking Jenise. And the presentation is open for discussion, both in typed and verbal questions. So there was the question is from Professor Hoang. How do you choose the number of ionic steps, NSW, for the system you are simulating? How many steps would be sufficient?
Of course. And this definitely depends on what sort of a system that you're simulating, whether that be a very complex system or a very, very simple system, such as, something simple like what we are showing right now up on the screen. Essentially, I believe that it's a little bit more, instead of being something that's very concrete, it's very sort of fluid in how many steps you can use, or how many steps you should use at least. In my belief, if you want a more accurate view of things, you'd want more steps. If you want something that's a little bit less accurate, you'd use less steps. Or at least that's sort of my view of things. So.
Okay. Let me contribute. Oh, okay. Yeah, Professor Hoang is happy with the answer. Yeah, if system is in equilibrium, it's not long. If it is a reaction, then one needs to wait until it is done. Lixue Shah is asking one question for Jenise. How to decide the value of S mass, or what is the difference between the S mass equals -1 and S mass equals 0? So basically, Lixue is asking what's the difference between heating, thermalization, and molecular dynamics. Can you explain it?
Heating, thermalization, and molecular dynamics. Okay, yeah. So heating thermalization, essentially, from my knowledge at least, where it differs from molecular dynamics, is in the fact that often this thermalization is, how do I say this? It's very limited in its use, and it's not often used for, how do I say this?
Okay. I would like to contribute to keep asking the same question as Lixue was asking. So we still need to bring it to make it absolutely clear. And I'm going to focus on the slide number 5 and ask about the lower right box. So you have a segment of the postcard that you have highlighted with blue box.
Yes.
Can you please explain what it is?
So these are, I believe, at least the velocities of the individual atoms at each time step, if I remember correctly. I'm not 100% sure on that, but from what I know at least, that is the sort of velocities that we'd be looking at, or at least like part of the trajectory, at least the velocity part of the trajectory that would be looking at.
So what would happen if you start as mass equals 0 without thermalization? Without heating? If you immediately take relaxed geometry and start molecular dynamics, what would be contents of this blue box, and what would be the image movie of the molecular dynamics to your expectation?
I would expect that it would be an optimization.
But if it is optimized, if it is already optimal geometry,
then I'd imagine that it would be a blank box. It would be all zeros.
Yes. And what will be how would movie appear?
Movie would appear completely still, absolutely no movement.
Super. To my understanding, it is the perfect answer to question of Lixue. Lixue, are you happy with this answer of Jenise, or you want more details? Okay, Lixue is telling thank you, so he's happy.
Thank you for the question. Yes.
And Mel has a question. Yes, please.
Actually, can you hear me?
Yeah.
Perfect. Sorry, my internet is really horrible here in Canada. So.
Mine is too.
In your molecular dynamics, could you go a slide before? Keep going. There's one where you had a bunch of wiggly lines on a graph. I had a question on that one.
Oh, is it the temperature graph? Temperature versus time graph?
Yep,
I think that's a little bit later in the slides, yeah.
Yeah, wherever you have that.
Oh.
Yes.
Oh, here. I think it is here.
Yes, there you go.
Okay, so this is a very interesting graph to me. So first, can you explain what it is we're looking at and what kind of behavior you expect to see after a certain amount of time versus temperature?
I would expect, at least normally anyways, that the sort of temperature would equilibrate down to, due to the potential sort of eating up that kinetic energy, though from what I'm seeing on the graph at least, although this is not a system that I particularly know off the bat, it seems to be shifting quite a bit. As to the reason why, I'm not 100% sure, if I'm being honest.
Well, it's okay because you're starting, you're just starting this out. What would be a way to kind of go forth in the file system? It looks like for me you have femtoseconds up to about 550. Mm-hmm. What would you do to, based on the character of the graph?
Based on the character graph, I would suggest doing a longer time step. So doing longer time steps all the way up to, probably, at least probably a couple thousand femtoseconds, at least.
I would agree with that because it looks like about 500 you start to spike up quite a bit. So, yes. And then what would it look like? You said it would equilibrate, so then it would just kind of look like what? If it was
it would sort of look like a gradual decay, essentially, or at least it would not look quite this chaotic, for sure.
So the spikes up and down would be like smaller.
Yes, correct.
Yeah, because you wouldn't be varying so much. Okay.
Yeah.
That's all I want to know. Thank you.
Okay, gotcha. Thank you.
More questions. There is a typed question from JOYANTA to Jenise. JOYANTA, would you like to ask your question? Please either type or speak to the microphone. Right now it looks like you are muted.
Question, small basic question, that what is the best visualizing tool for molecular dynamics? Like, what is the best molecular visualizing tool? Like, if you consider Avogadro and visualizing molecular dynamics, BMD, which is the best visualizing tool for molecular dynamics?
I would say, personally, at least from the ones that I've used, I believe VMD is very robust. Although it lacks a lot in sort of more visual cases and can often sort of chug sometimes, I believe that the analysis toolset that it provides is very useful. It's a very useful toolset. And so I believe that since it's so robust, that can often make up for some of the visual issues that are noted occasionally in VMD, as opposed to some of the more visually oriented softwares.
Yeah, all right. Yeah, thanks. Great. Yeah. Okay, great. Thanks. Yeah. Great. Yeah.
Okay.
Great, yeah.
More last chance for questions to Jenise. More questions 1. More questions 2. More questions 3. Okay, let's thank Jenise once again. And congratulations to all participants of the class, all visitors, participants to the questions for support and for enthusiastic and intellectually intense semester. So there is a hope that skills accumulated during this semester will be very helpful towards practical research components, and the presenters will hear from me about the grades for these presentations and for the semester very soon. But being brave and presenting this important amount of information and answering questions is credited substantially. So many thanks to everyone, and thank you to all participants.
Thank you, Dr. Singh.
Thank you very much. So from now on, the presentations are done and semester is done. So everyone is welcome to disconnect, and I will check if recordings went good. If they were accessible, they will be shared with all participants.
So this is the last class for us?
Yes, we need to stay in the schedule of the semester, and summer semester is over. If you are interested to continue this activity, let me know. We can find some format. But
I can still use the photon, right, anytime.
If you need to access the facilities, send an email to me, and it would be very possible.
Oh, okay.
Okay, I'll stay connected for a few minutes if there are some follow-up questions, but we are done for the semester. There are no any more required steps, and everyone is welcome to disconnect if willing to do so.
Awesome. Well, awesome. Congratulations, everyone, and I'll see you guys next time. And I'll probably be I'll be in Halifax when I connect with you.
Oh, thank you. Many thanks. It's really great. Thank you for continuous support and visiting sequence of these events. The
absolutely.
Unbiased questions are the critically important part of this course.
Yeah, no, and absolutely, and it's really relevant to what I'm doing, what I'll be doing experimentally. So this is going to be really useful to still continue and grow from where I was. So it'll be really quite useful.
Mm-hmm.
And yeah, all right. Well, everyone stay safe, and I'll see you next time.
Yeah, see you.
See you.
Okay, thank you, Tao. Thank you, Lixue. Thank you, Steven. It was really great. Yeah, a couple of people are connected, but we are going to disconnect now. So if there are no special questions to me, I'm going to disconnect. Thank you, Lixue. I look forward for fruitful collaboration with your advisor, Professor Taoyu, and